Today I will be doing a screencast on DC circuits. Specifically, I will be talking about elements in series and elements in parallel. Elements are in series, the current must be the same throughout all the resistors. This is represented by the equation I1 equals I2 equals I3, which equals I total. In addition, the voltage total, or the electrical potential difference, is the sum of the different voltages at different points. That is represented by the change in V1 plus the change in V2 plus the change in V3 equals the change in V total. Resistance is also equal to the sum of the different parts, as represented by the equation Req equals R1 plus R2 plus R3. One of the ways we can conceptualize this series circuit is by a water analogy. In general, a different amount of gravitational potential energy is lost when the water flows down. However, the current is the same everywhere, which is representative of the current equation, and the voltage total is the sum of the parts, just like the gravitational potential energy. The total here is the sum of these individual parts. Let's take a look at the circuit simulator to get a better understanding of how this series circuit works. Okay, so we'll use this non-contact ammeter to check the reading of the current over the wires. It's 0.45 amps here, 0.45 amps here, and 0.45 amps here. And this makes sense because we know that the current is equal at all parts of the elements in the series. And we know that the potential difference, or voltage, is different at different parts, and the sum of it will equal the total voltage. So over here we can see that it's 4.5 volts, and over here it's also 4.5 volts. So then the total voltage is 9 volts, and 4.5 plus 4.5 is 9, so you can see how that is the sum. Some disadvantages to series circuits are that if one bulb goes off or is turned off, then all of the light bulbs in that series will not work because the circuit will not be complete. In addition, each resistor operates at less than the battery voltage, so this means that less power is delivered to all the bulbs. Elements in parallel are another way that the elements can be arranged. In parallel circuits, the current is equal to the summation of the other currents, as represented by this equation, I1 plus I2 plus I3 equals I total. The change in voltage, however, or the electrical potential difference, is equal to one another at different points. And as you can see, this is different from in series. Also, there's an inverse relationship, so 1 over the resistance equals 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance. A water analogy that you can apply to elements in parallel is water flowing out of a dam. When water flows from a dam, the gravitational potential energy lost per kilogram of water falling into the rest of the water is the same despite the path that the water takes. So this is similar to the voltages across the parallel resistors since they equal each other, regardless of their path. Let's take a look at a parallel circuit using the simulator. We know that the current total is equal to the sum of the parts, so let's check. 0.9 amps, 0.9 amps, and 1.8 amps. And this makes sense because 0.9 plus 0.9 is 1.8. Okay, and the voltage should be equal to each other. So this is 9 volts here, this is 9 volts here, and this is 9 volts here as well. Okay. Elements can also be in series parallel combinations, which is a combination of the series and parallel circuits. To solve problems involving series parallel combinations, you have to separate and reduce the circuit in order to calculate the different values that you might need. So I think it's easier to start with the elements that are smaller. So first, you have to determine which groups of resistors are in series and which are in parallel, and then you can reduce the groups into equivalent resistances. And then you have to reduce the circuit further to treat the separate equivalent resistances as individual resistors. And you keep doing this until you have a single loop with one total resistance value. And you can find the current of the reduced circuit using I equals V over R total. And then you can expand the reduced circuit back to the actual circuit when you reverse the reduction steps. And then you can use the current of the reduced circuit to find the current and voltages for the resistors in each of the other steps. Here is an example of a circuit incorporating both series and parallel, and this is using the circuit construction kit. You can see that these two elements are in parallel, whereas these are in series. Okay, thank you for watching.